biomechanical design is a very exciting domain, which we're going to explore with a thought leader in this domain, James Shippen. You're the director at Biomechanics. And can you explain a little bit for users who don't really know what it is and how it's deployed?
Fine. It's a branch of engineering. You would have automotive engineers who analyze vehicles. You'd have nautical engineers who analyze aircraft. Biomechanical engineers are exactly the same background, but they analyze a machine that's a bit more complicated than an aircraft, and it's made out of weird material, but the maths is the same as an aircraft and a vehicle. It just happens to be a human body. And all of the same maths, Newton and Lagrange, apply to us as much as they do to an aircraft or a vehicle.
Yeah, and I used it already before, mainly in sports,
Sure.
but it's applied in many domains. Can you explain a little bit how it is applied in this domain?
It is a very broad subject. It's basically any subject where you've got people interacting with the environment or equipment. So, for example, ergonomics. How it's best to say move equipment, push equipment, lift equipment. What we can do is start looking at what the implications of that is and what the potential injury risks are for that. So ergonomics is large. You mentioned sport, very large applications in sport. In terms of three basic routes, there's the performance side. So why is that athlete better than that athlete? What can that athlete learn from that athlete by having quantitative data to compare? You've also got injury prevention, which is you're loading that joint much too much. There's going to be problems there. Just change it a bit and there's a chance you will avoid the injury. You've then got post-injury, so there's a return to play. When are you fit to go back on the field? So if you're paying these guys, God knows, £100,000 a week, you want to get them back on as fast as possible, but you don't want to put them too soon. So that's another application of biomechanics. Mentioned automotive. There's things like getting in and out of the vehicle. How easy is that? So that is a question for biomechanics. And there's also the research aspects. Bob's used a lot in various universities around the world for, I can't even think what they're doing, but they are using Bob, which is a musculoskeletal model. So anything you want to use it for, it's yours.
Yes, the key part of this is fidelity.
Correct, absolutely.
Having more details, and based upon this data, you can take better decisions.
You've got it, exactly. So biomechanical analysis does go back to 70s or so, when it was just stick figures moving. So in that respect, it's very low fidelity. It's literally just what you'd do on a piece of paper. Over the last, 50 odd years, it's advanced from that. So now what we've got is the whole skeletons in there, and also we've got all the muscles are in there. So in the human body, or within Bob, you've got about 600 muscle units that you've got in there. So it's a reasonably high fidelity. Having said that, it's going to get better. It's a very fast advancing subject. So within 10 years, I would imagine we're going to have an even more high fidelity model.
So you were talking about musculoskeletal. Can you explain how this is applied and how is this different?
Absolutely. A typical workflow would be a motion capture you'd start off with. So you might have seen when they're making video games, they got all these little ping pong balls all over the subject, and they track them with loads of cameras. We can pick up on that data, and that's very good positional data. The problem with that is it works well in a lab, but if you get out onto a sports field, you've got numerous problems. What's happened in the last 5 years or so, they've come up with another system for motion capture that uses accelerometers and gyroscopes, and in little units, about so big, you cover the body with that. And there's also video stuff. But basically, you would start off with motion capture. Can I just cut back before motion capture? You've got to have a good question. That's often the critical part. You've got to ask, is this a question that's answerable by musculoskeletal? Let's say it is. You want to know why this vehicle is difficult to get in and out of. So Okay, got a good question. You then do motion capture of people getting in and out of that. What you then do is look at, okay, well, why is that vehicle better than this? Is it to do with the loads on the joints? Is it to do with how much torque you got to apply? Is it how much you're twisting or not? So this is the kind of quantitative data that you're passing over to the design engineers in that case. Before that, all you'd have is basically eyeballing somebody and saying, okay, well, that looks a bit strange. But now we've got the quantitative data, and that's really the big advance that biomechanics provides.
Here we're talking about the design engineers. What kind of typical challenges are they facing in biomechanicals?
Yeah, numerous. Is the quality of the motion capture. As I say, that's getting better, but it's still not there. A latest thing that's happening is using AI with video cameras, and that if that comes off, that will be a big advancement. That's not quite ready yet. The stuff that we're made out of is very strange. You know, I envy automotive engineers. They've got steel. We don't understand steel. That stuff is not steel. That stuff is weird. Yeah. So we need good models for the materials. What you also need is to understand how the body is working. I can hold my arm out like that, but I'm activating loads of muscles around there, and I could do it in a different way. How does the brain decide which muscles to activate? We've got approximate descriptions of what the body's doing, but it's not the final model. So we've got to get better on that. Also, things like fatigue. At the moment, fatigue is not well understood as regards musculoskeletal modeling. So we've got to improve that in terms of the models. So we fully acknowledge we're at a stage where we can provide quantitative information, but it's not the final step. We've still got a lot of questions to go, and I suspect we'll never finish.
We never finish, of course, because you can always get better and more data. But what can we expect in the coming 3 years? What kind of improvements are there, and how can organizations and all the engineers in the domain benefit?
I think that the biggest advance in the short term, i.e. of 3 years, is going to be on the motion capture side. Previously, when the days of the ping pong balls, we used to use that, and we would take out literally a truck to go out and capture motion data. What you're going to be doing in 3 years' time is using one of those. Yeah. And also, the ping pong ball approach was costing £150,000 by an app.
Yeah.
And that's going to revolutionize the world.
Very, very exciting. Looking forward to talk with you in a couple, next year and see how it evolves. James, thanks for your insight. And thank you here watching for MATLAB Expo here at Silverstone in the UK.